So we've looked at how the rate of a reaction depends on the concentration of the reactants. Now we're going to look at temperature because most chemical reactions are highly sensitive to temperature. For a typical biological reaction, an increase of 10 degrees Celsius can double or even triple the rate. And if that's, happening in your body, that could be a big problem. So the rate constant K is only a constant when the temperature is constant. So if the temperature changes, then we have to find a new rate constant at that temperature. Rate constants generally increase with temperature. Most reactions go faster with higher temperatures. This is the Arrhenius equation. I don't care if you remember the name. It's named after a Swedish scientist. So this is our rate constant K, and this shows the temperature dependence of K. So the rate constant is equal to a frequency factor times E raised to the power of negative activation energy over the ideal gas constant times the temperature in kelvins. It's a bit complicated. So let's talk about that activation energy and that frequency factor. So here we have an energy diagram showing the energy of the reactants and the energy of the products. Is this reaction exothermic or endothermic? It's exothermic because the energy of the reactants is higher. The products are lower in energy. Where did that energy go? It left the reaction. It went into the system. Into the surroundings. So again, looking at this very simple 2H2 plus O2 making water. So here we have our reactants. And in order for them to actually react, they have to collide and they have to have enough energy. So this is the activation energy from the original energy of the reactants through this hump. That's EA. The frequency factor is how many times per second or per unit time the reactants approach this. So I think of this a little bit like miniature golf. Let's see. So here's a giant person, right? And they're playing miniature golf, right? And you hit the ball and you're trying to get it up over the hump, right? If you don't hit it hard enough, if you don't give it enough energy, it doesn't go. It just comes right back down. And then you try again, right? Some people get really impatient and they'll just go whack, whack, whack as soon as it comes back down, right? And other people are going to take their time. So the frequency factor is how many times the reaction tries to go over the hump. The activation energy is how tall the hump is. Here's a very simple reaction where methyl isonitrile rearranges to form acetonitrile. And this is really kind of a funky reaction because what's happening is the nitrogen and the carbon are switching places. That triple bond stays the same, but the nitrogen loses its bond and the carbon gets the bond. So we go from this guy to that guy. The molecule goes through a high energy intermediate state. In order for the reaction to occur, the nitrogen bond has to break and the carbon bond will form. So originally, this nitrogen is bonded to this carbon over here, and this is the bond that needs to be broken. So we need to weaken this and allow this group to rotate. So this carbon can come over here. So this is an activated complex, which is higher in energy. This bond is kind of in an intermediate state, and this is in the process of switching over, of rotating. So the activation energy is the energy needed to reach that activated complex or transition state. When it gets to this point, it's kind of teetering. It could go either way, right? This could rotate and the carbon could bond with the carbon, or it could rotate the other way and the nitrogen could bond with the carbon again. But the higher the activation energy, the slower the rate, because you need more higher energy particles to get over the hump. Any questions yet? So what about the frequency factor? The number of approaches per unit time. So for this particular reaction, this NC group begins to rotate. And they call it wagging, like a dog's tail, right? So it vibrates side to side, and the frequency factor is related to the rate at which it's wagging its tail. Each wag is an approach to the activation energy, activation barrier. If it wags with enough energy to get all the way up here, then it can go forward and react. If it doesn't quite work, it comes back down. I just thought of another analogy. So, swinging on an old-fashioned swing, right? Do you ever think, I wonder if I could swing high enough to go all the way over, right? You can't, but it's fun to dream, right? But when you get higher and higher, you're like, oh, I'm getting close, and you come back down. Because you haven't reached that point where you could go either way. But at the very top, if you were able to get there, you would stop for an instant, and it would be possible to come back the other way. So that's kind of what this activated complex is like. And then there's that exponential factor. That's the fraction of molecules that have enough energy to make it over the activation energy on a given approach. So that's going to be a number between 0 and 1. So it's the fraction of approaches that are successful and result in product. So if we had, So the frequency factor is that is the A term in the Arrhenius equation, where the rate constant is equal that frequency factor times E to the negative EA over RT. And this guy right here is the fraction that they're talking about. So if this is A and this is the exponential factor, E to the fraction, then you multiply those two, and that gives you the rate constant. So in this case, it would be 100 per second. And that would be the number of approaches that are successful. Any question? So the exponential factor depends on the temperature T and the activation energy. It's E to the negative EA over RT. So if, and it's negative here. So we want this number to be smaller to make our factor larger. E to the negative small number is bigger than E to the negative big number.
What's the R?
R is the ideal gas constant.
Oh.
Yeah, old friend, right? He's still around. He's got different units, but you saw those two in Chem 1A. Yeah, just good old gas constant. So if EA is small and temperature is high, so here in the fraction, the numerator is small, the denominator is big, this entire factor becomes a small number, e to the negative small number approaches 1. Every approach is successful. When you have high activation energy and low temperature, this exponential factor, this whole thing approaches 0, where no approach is successful. So temperature is the average kinetic energy of a substance, but it's the average. Molecules in a sample have a range of temperatures. Some are higher than the average and some are lower than the average. So this is a temperature or thermal energy distribution. So the fraction of molecules with that amount of energy against energy. So we have T1 and we have T2. And it turns out that as the temperature increases, the energy distribution gets wider. Temperature gets smaller, it gets skinnier. What we're interested in is how many of those molecules have an energy greater than the activation energy. So even though the average is over here, when we increase the temperature, this long slope moves over, and now we've got this whole orange area here as opposed to just the blue area. And so we're going to have a higher it's going to react faster. Summary. Frequency factor, number of times the reactants approach the activation barrier per unit time. Exponential factor is the fraction of approaches that are successful. The exponential factor increases with increasing temperature, but decreases with increasing activation energy. So it can be kind of confusing looking at all of those, AE to the blah, blah, blah. But if we just think about it as really about the person playing miniature golf. The harder you hit the ball, the more likely it is to go over. How hard you hit the ball is how much energy it has. That's related to the temperature of the substance. How frequently you hit balls at the hump also affects how many will go over. Because if you just hit one ball every hour, you're not going to get very many balls over the hump, right? But if you hit one every second, you're going to get a lot more over. Just, odds. So if the hump is taller, will the reaction go faster or slower? It'll go slower. Because fewer molecules are going to have enough energy to go up and over. So the temperature increases, meaning, and actually that frequency factor also increases with temperature. So the rate constant increases with temperature and it decreases with increases in activation energy. So which statement best explains why reaction rates generally increase with increasing temperature? A, reaction rates increase with increasing temperature because as temperature increases, a greater fraction of molecules have enough thermal energy to surmount the activation barrier. Does that sound correct? That sounds pretty good. Let's read the others. Because as temperature increases, the pre-exponential factor of the rate constant increases. Oh, we didn't talk about that really, did we? That's the frequency factor. Or the reaction rates increase with temperature because As temperature increases, molecules decompose into their constituent atoms, which can then form new bonds to form the products. That sounds like something somebody made up, doesn't it? So this is definitely not right. So this is the correct answer. So if you haven't noticed yet, scientists like to graph things, right? We like to take an equation and figure out how we can put it into a linear form. That's what those integrated rate laws were about. How can we take this data and graph it in a way that gives us a straight line? So this looks like a big old mess. But we can rearrange this into a linear form. The natural log of the rate constant is equal to negative activation energy over R times 1 over T plus natural log of A. And what was done here is they took the natural logarithm of both sides of the equation. So here, the natural log of K is on our y-axis, 1 over T is on our x-axis, and this is our slope. The intercept is the natural log of A. The natural log of A, this factor is really its temperature dependence is small. It does have temperature dependence, but it's small. And so a lot of times we ignore it. And since we're just starting out in this, we have the luxury of saying, we're going to ignore that. So how do you use an Arrhenius plot? This is the equation or chemical equation describing the decomposition of ozone, which is important in many atmospheric reactions. The ozone falls apart into O2 and an oxygen atom. So they studied the kinetics of this reaction, and they found the rate constant at different temperatures. Okay, so they found the rate constant at different temperatures. So what we're going to do is we're going to graph the data. Oops. It doesn't, that slide doesn't say what, oh, it does. Okay. Back up. There's the study. Determine the value of the frequency factor and activation energy for the reaction. Kind of skipped over that part. I'm like, what are we supposed to do here? We're trying to find the frequency factor and the activation energy. So the hard work of graphing this has already been done. You take the natural log of all your rate constants. You convert your temperatures to Kelvin, and you go 1 over Kelvin. And you graph them, and you get this line. And here's the equation that Excel gives you. And so the natural log of K is equal to negative EA over R times 1 over T plus natural log of A. We pull 1 over T out here because this is the X variable, and we want to make sure that it's not lost in here. So if we're trying to find the activation energy, what number out of this do we need? We need the slope, right? So the slope equals negative EA over R. So if I multiply both sides by R and multiply both sides by -1, I come up with the activation energy is equal to negative slope times R. So you really have to be careful with your negative signs here. There's our slope. The slope itself is negative, but we want the negative of the slope. And we're going to multiply by R, and we're going to use 8.341 joules per mole Kelvin. The units here do work out, but I don't see the point in messing with them. So if we take 1.12 EE4 times 8.314, it's 314, right? Not 341? Yeah. I get 93114.8. Anybody else get that? I'll do it again. Nope, I got a different number that time. I'm going for best 2 out of 3. First answer wins. Did anybody get that?
Yeah, I got it.
Okay, thank you. I thought I was going crazy.
I got 93116.
Yeah, I did too.
6.8.
Let me try it one more time. I'm still using my crunchy calculator. Yeah, now I got 93116.8. What would the unit on that be? Joules. So this slope is the rise, the natural log of K, over the run, which is 1 over the T. And so this is really ends up being joules per mole. And that's a ridiculous number of significant figures, so we should probably call it 9.31 times 10 to the 4th joules per mole. How do we find the natural log of A? The slope equals the the intercept equals the natural log of A, right? So the intercept is 26.8, and that equals the natural log of A. To get rid of natural log, we do e to the x of both sides. We end up with e to the 26.8 is equal to A. 26.8 4.36 times 10 to the 11. pull the script down far enough. That's one of the simplest problems I've had all semester. What might the units on that be? Yeah, s to the negative 1 would be the logical choice because it's a frequency factor. It's how many approaches per unit time. Any questions?
So the slope, the units on that exactly was natural log of k or
It's the units of natural log of k.
units of natural log of k.
And when you take the natural log of things, units kind of go into Never Never Land,
Okay.
right? So this is 1 over whatever the x units are, which is 1 over t. So that ends up being t. So if this has units of Kelvin, that Kelvin cancels this Kelvin, and I get joules per mole. So for the decomposition of ozone, use the results of Arrhenius analysis to predict the rate constant at 298. So we need the results. And still my calculator, A was 4.36 times 10 to the 11th. E to the A was 9 something. Anybody write it down? 9.31 times 10 to the 3rd? To the 4th. And that's in joules per mole. Okay. So if we want, dang it, there we go. If we want to find the rate constant, we're just going to use the Arrhenius equation, which is E, K is equal to A times E raised to the power EA over RT. So this is going to be equal to 4.36 times 10 to the 11th times E raised to the negative 9.31 times 10 to the 4th. The gas constant has units of joules, and so I want to use this in joules and not kilojoules. That's a common problem. Joules per mole, Kelvin, and that's going to be divided by R, 8.314. Sorry, those are the units of the rate constant. And the temperature is 298 K. So what happens to all those units? They cancel out, right? And so now we have to figure out how to do this on our calculators. And it's going to be different depending on what kind of a calculator you have. So some of them you can just type it in as it looks. I'm dealing with a TI-30XA right now, and so I have to do the exponent first and then do e to the A of that. I had it, and then I pushed a button, and it all went away. Of course it did. So I'm getting
Close.
2.09 times 10 to the minus 5.
Yes.
Yes. That's what I got.
Awesome. So if you're having an argument with your calculator, I'll talk to your calculator during lab, and we'll get it to shape up, okay? Any questions other than how did you get your calculator to do that? Someone asked me that on YouTube the other day. Well, there's an instruction manual for your calculator. Go look it up. Yes?
For the answer on the PowerPoint, it says the units per K are m to the negative 1 times s to the negative 1. I was wondering how we get that from what we plugged in.
That's a good question. Oh, see, I did them there. Let's see.
Because it already gives us the rate constant.
Well, the units of K depend on the order of the reaction. So I'm guessing that this is a first order reaction, and that's why the units are what they are. Yeah. So sometimes graphing is a little beyond what you want to do. So you can calculate the activation energy from the rate constant at 2 different temperatures. And this is something we're going to do with the data from our experiment that we're doing today. If you only have 2 data points, there's no point in making a graph, no pun intended. You can just use this equation. And this is basically taking the coordinates of one point and the coordinates of the other point and sticking them in and mixing them up, right? So natural log of K2 over K1 is equal to negative EA over R, 1 over T1 minus 1 over T2 minus 1 over T1. Consider this reaction between nitrogen dioxide and carbon monoxide. Okay, they're giving us a rate constant. Rate constant, oops, that's the temperature, at 701 Kelvin is measured at 2.57. So let's call those 1. And then there's K2 and T2 at 895 Kelvin. The rate constant is 567. And they want us to find the activation energy. So our equation is natural log of the quantity K2 over K1 is equal to negative EA over R, 1 over T2 minus 1 over T1. This equation has lots of pieces. It's got a natural log in there, and you've got subtracting fractions. You don't want to rearrange this one first. You want to take your numbers in, stick them in, and then deal with it and straighten it out. So we've got natural log of, and we have to be careful and get our 1s and 2s straight. 567 divided by 2.57. That equals negative EA, the thing we're trying to find, over 8.314. T2 is 895. And T1 is 701. So 567 divided by 2.57, e to the x. Nope, wrong already. Try that again. I did e to the x instead of natural log. I thought that number was really big. $5.408 for the left side. Anybody else get that? A couple of nods. Then let's do that fraction thing. And we don't need to do what you do in math class where you find common denominators. And you just 1 divided by 895 minus 1 divided by 701. And I'm getting negative 3.09 times 10 to the minus 4. Anybody else get that? Anybody? No? Okay, let me do it again. 1 divided by 895. 1 divided by 895 minus 1 divided by 701.
I got the right side, but I didn't get the left side.
Yeah, the right side's right, but for the natural log of K2 over K1, I got 5.39.
Me too.
No, 5.39. Okay, I'll do that one. Five, 6, 7 divided by 2.57 equals natural log. Yeah. 5.396? Okay. Thank you. So what I want to do here is I'm going to take my 5.396, I'm going to multiply by 8.314, and I'm going to divide by the 3.09 e to the minus 4, and I'm going to get a crazy looking number. EA is 1.45 times 10 to the 5th. What are the units? Well, the units on the gas constant are determining what the units are. So what energy unit is used in this gas constant? Joules. So this is in joules. The question asks for kilojoules per mole. So that's going to be 1.45 times 10 to the 2 kilojoules, or 145 kilojoules. Good way to practice these. This question is in the book. It's example 15.8 from your textbook. And you go to the book, you look at it, there's nothing, no helps there or anything. You try to do the problem. You can check your answer in the back. If you're not getting it right, pull up the lecture video. Hopefully the one that's on Canvas is better than this one is turning out. So you can watch a little bit and figure out what to do next. Okay, so they rounded to 2 significant figures. Not sure why, doesn't exactly matter. Use the results from example 15.8 and the given rate constant at either of the 2 temperatures to predict the rate constant for this reaction at 525. Oh, I thought I had written it down like last time, but no. So EA was, let's just use what we had, was 1.4 something? 4.5 times 10 to the 5th joules per mole. And we're going to use K1 and T1 from the previous slide. I happen to remember the first one and not the second one, so I'm using that one. We want to find K2, and we know that T2 is 525. Everybody okay with how I got those numbers? Did I copy them down right? So the equation K2 over K1 is equal to negative EA over RT, 1 over T2, minus 1 over T1. It doesn't matter which point you call 1 and which point you call 2. It'll work either way. But one way's easier. It's easier to find the numerator here than the denominator. So that's why I set it up like that, because I've done this before. So let's plug the numbers into that equation. Natural log of K2 over 2.57 equals negative 1.45 times 10 to the 5th. I want to use the joules instead of kilojoules because of the gas constant. One over T2 1 over T1. What happens with the units here, I've got joules per mole divided by joules per mole, those cancel out. This is 1 over K, which is the same as K, and that cancels out the 1 over K in there. The natural log has no units. Okay, so we can calculate that stuff on the right side. This is a good place to use those parentheses. So the natural log of k over 2.57 equals negative 8.341. So I'm going to take the natural log of both sides of this equation, and I'm going to get k2 over 2.57 equals e to the negative 8.341. E to the negative 8.341 is 2.4 times 10 to the minus 4. And then I'm going to multiply by 2.57, the denominator on the other side. And I'm going to get a rate constant that is 6.13 times 10 to the minus 4th. This rate constant will have the same units as the other rate constant. Anybody else get that? Okay. Is that answer reasonable? We had a rate constant at 700 that was 2.5. 525 is lower in temperature. Do we expect the rate constant to get larger or smaller? Smaller. And it did, it got smaller. So that's not proof of anything, but it's encouraging. Ooh, that's also encouraging. Reaction A and reaction B have identical frequency factors, but reaction B has a higher activation energy. Which reaction has a greater rate constant at room temperature? Yeah. The higher the activation energy, the slower the rate. And rate constants are proportional. So A. I kind of alluded to this earlier, the collision model. If we look at the frequency factor for a reaction where we have two gas phase reactants, A and B, instead of the one molecule where it was wagging its tail, now we have two things that have to collide. The chemical reaction occurs when you get a significantly energetic collision between two reactant molecules. Each collision represents an approach to the activation barrier. So the frequency factor is usually less than the number of collisions per second. Any ideas why? In this example, these have to collide with the right orientation to react. If they collide back to back, they're not going to react. So not all the collisions count. So we watched the video, and in it he explained a whole bunch of stuff. But he explained about how the position, the orientation matters when things collide. So the frequency factor, A, that we were just looking at, has two parts to it: an orientation factor and a collision frequency. So the orientation factor is the fraction of collisions with favorable orientation. It's going to be between 0 and 1. And the collision frequency is number of collisions per unit time, typically about 10 to the 9th per second. Molecules are busy little boogers. So here we have pictures showing ineffective collision, effective collision. They have to collide in the correct way in order for reaction to occur. Here, that orientation factor is only 0.16. So 16% of collisions are in the correct orientation. So a small orientation factor, a small fraction of collisions that are oriented correctly, must be aligned, means that things must be aligned in a very specific way. When we have reactions between atoms, two atoms bumping into each other, those usually have an orientation factor close to 1, because atoms are spheres. They don't have a front side and a back side, right? No matter how you hit them together, they're oriented correctly. And then, just to be weird, it's possible for the orientation factor to be greater than 1, and that indicates that an actual collision is not necessary. So here, which reactants do you expect to have the smallest orientation factor? The smallest fraction of collisions that go together correctly? Are we looking for most complicated or simplest?
Complicated.
Right, complicated. Because the more complicated it is, the fewer collisions end up being correct. Well, this is between two atoms, so that's going to have a large orientation factor. Looking at these two, these are both diatomic molecules. Here we have hydrogen, two hydrogens, and two iodines. So if this one comes in like this and this other one comes in the opposite orientation, is it still going to be okay?
Yeah.
Yeah, because one side is the same as the other side. There's some symmetry. Here, if I change one of these around, then it's a completely different orientation. So which one's going to have the smaller orientation factor?
C.
C.